Okay, so we are back again. So whenever starting that's your next lecture, just starting from the beginning of the previous one, right? So some just such that things will be easier for all of us. So the flux linkage equation, then psi d, psi q, and psi 0. This already we have seen in the previous lecture, but just we have to move further. So psi d will be minus L d I d plus L A F d I F d plus L A K d I K d after your transformation. Then psi q also will be minus L q I q plus L A K q I K q, and psi 0 will be minus L 0 I 0, right. So now next we will see the rotor flux linkages in dq0 component, right. So substitution of the expression for id iq in equations 53 to 55, if you make everything, then we will find that psi fd will become L ffd ifd plus L fkd ikd minus 3 by 2 L afd id. What I suggest that whenever you listen to the lecture, you please keep the list of nomenclature with you, because so many terms are there, right, like your mutual inductance between stator and rotor, then self inductance of stator, self inductance of the rotor circuit, right. So similarly your psi kd will be L fkd ifd plus L kkd ikd minus 3 by 2 L akd id, and similarly psi kq will be L kkq ikq minus 3 by 2 L akq iq. Now question is that if we put everything in the 3 into 3 matrix form and simplify, you will get like this. But as to save the time, directly I have written all these things, right. Otherwise it will take long time. But as an exercise, you please try yourself, you will find hardly it will take few minutes to derive that. So again all the inductances are seen to be constant, that is they are independent of the rotor position. Here the psi fd, psi kd and your psi kq, they are independent of theta, right. So it should, however, we noted that the saturation effects are not considered here. We will not consider the saturation effect throughout, right. So now it is interesting to note that I0 does not appear in the rotor flux linkage equation. This is because zero sequence component of armature current do not produce the MMF across the air gap. This you should keep it in your mind. Now while the dq0 transformation has resulted in constant inductance in equation 64 to 69, right, they are independent of theta. The mutual inductances between stator and rotor quantities are not reciprocal. Reciprocal means, for example, when you have studied say transformer, when you make per unit values, then either it is referred to primary or referred to secondary, it is same per unit values, but in this case it is not, right. So later we will see, we will see some mechanisms such that both can be made it same, I mean either to the stator side or to the rotor side, right, when you make the per unit system analysis. For example, the mutual inductance associated with the flux linking the field winding due to the current id flowing in the dx stator winding from equation 67 is 3 by 2 L afd, right. Whereas if you look into equation 64, you will find the mutual inductance associated with flux linking the dx stator winding due to field current is LAFD. It is 3 by 2 LAFD and it is LAFD. So it is not reciprocal. Reciprocal means they are not same, right. So this problem is overcome by appropriate choice of the per unit system for the rotor quantities, that we will see later. Now next is, this already we have seen in the previous lecture, but started with this only. So stator voltage equation in dq0 component. Now equation 26 to 26 are basic equation for phase voltages, right, that we have seen earlier in terms of phase flux linkages and current. By applying the dq0 transformation of equation 59, the following expressions in terms of the transform components of voltage, flux linkage and currents results. I mean all the derivations, not putting it here because I told you again and again that it will take long time. I suggest you try to make yourself, and certain things you should keep it in your mind. For example, this you should keep it in your mind. For example, then in this case what will happen, ed will become p psi d minus psi q p theta minus ra id, right. So this is p is d dt, so it is d of dt psi d, right. So this is later it is explained, this is actually one term called your transformer induced voltage. This is p theta, that is d theta by dt, that is speed voltages, right. And similarly eq is p psi q plus psi d p theta minus ra iq, and E0 will be P psi 0 minus Ra into I0. This is equal to 70, 71 and 72. This is actually, keep it in your mind, but try to derive of your own. All derivations are not given here because it will consume then many hours, right. So, the angle theta as defined in figure 9, earlier I told you, right, and you see the figure 9 also, everything is drawn there, that angle between the axis of phase A and the d axis, the term phi theta in the above equation actually it represent, I will come to that, right, that the angular velocity omega of the rotor, that is d theta upon dt is equal to omega r, and omega r will be basically omega s because it is a synchronous machine, right. So, for a 60 Hz system under steady state condition, p theta will be omega r is equal to omega s because it is both are same. So, it will be 377 electrical radian per second. Now, the above equation have a form similar to those of a static coil except for the psi q p theta and psi d p theta terms, right. The result from the transformation from a stationary to a rotating reference frame and your what you call that represent the fact that a flux wave rotating in synchronism with the rotor will create voltages in the stationary armature coil, right. Similarly, this, for example, the psi q p theta and psi d p theta, psi q p theta means psi q into d theta dt, and similarly psi d p theta means psi d into d theta dt, right, are terms referred to as the speed voltages because it is d theta dt in general, right, due to the flux changes in space voltages, and that is your due to the flux and your p psi d and p psi q we call transformer voltages due to the flux change in time, because we know d psi by dt. So, it is p psi d means your d psi d dt, and this is d psi d d psi q dt, right. So, the speed voltage terms are the dominant components of the stator voltage, that is d theta by dt term. Under steady state condition, the transformer voltage terms p psi d and p psi q are in fact equal to 0, right. So, there are many transient conditions where the transformer voltage terms can be dropped from the stator voltage equation without causing error of any significance, right. However, in other situations they could be important, right. This is actually, just hold on. So, just hold on. So, in this case what happened that however in other situations that's this is something written section 3.7 5.1, it is not for you, right. Now the signs associated with the speed voltage terms in equations 70 and 71 are related to the sign conventions assumed for the voltage and flux linkage relationship and to the assumed relative position of d and q axis, right. We have seen the q axis actually leading the d axis by 90 degree. The voltage Eq in the q axis is induced by the flux in the d axis, right. Similarly, the voltage Ed is induced by a flux in an axis lagging the d axis by 90 degree, that is the negative q axis. Therefore, the voltage induced in the q axis due to rotation will be plus omega psi d, and that in the d axis will be minus omega psi q. This should you keep it in your mind. Now, electrical power and torque. Now, the instantaneous three phase power output of the stator is that generally we know Pt is equal to EIA plus EBIB plus ECIC. Now, if you make this all these things, your transform the D and EQ, your DQ0 transformation, eliminating phase voltage and currents in terms of DQ0 components. I mean, you substitute all, right, wherever EA, IA, EB, IB, EC, IC all in terms of your DQ component, and if you simplify, then you will get P by 2 will be 3 by Pt will be 3 by 2 into ED plus EQ plus 2 E0 73. This also you should keep it in your mind. It will be 3 by 2 into ED plus EQ plus 2 E0 After making all this, all the substitute all and simplify, then only you will get this one, right. And under balance operation E0 is equal to 0. Therefore, the expression for power is given by 3 by 2 ED plus EQ, right. Now, using equation 70 to 72, right, to express the voltage component in terms of flux linkage and currents by recognizing omega r as the rotor speed at d theta by dt and rearranging we have. Now, here what you do, that Ed, Eq expressions are known to you, you put everything in this expression, because that is equation your 70, 71 and 72, put everything and you substitute here. If you do so, you will get this term 3 by 2 into your Id p psi d plus Iq p psi q plus 2I0 p psi 0 plus psi d Iq minus psi q Id into omega r plus minus in bracket Id square plus Iq square plus 2I0 square bracket close into Ra. This is equation 74. This expression you will get, but each term has separate meaning. For example, the first term, that is your Id p psi d plus Iq p psi q plus 2I0 p psi 0. This is actually rate of change of armature magnetic energy, right? This is the first term. Now, second term is more important. Second term is psi d Iq minus psi q Id into omega r. This is actually, second term is the power transferred across the air gap. This term is the power transfer, your transform across the air gap. And third one, that is Id square plus Iq square plus 2I0 square into Ra. This is nothing but the armature resistance loss. So, this is the first term has some significance, second term also, third term also. That is why it is written, first term is rate of change of armature magnetic energy, plus second term is power transfer across the air gap of the machine, and third term is the armature resistance loss, right. Now, therefore, the air gap torque, we know P in general, power is equal to torque into angular speed, that we know, right. Therefore, the air gap torque Te is obtained by dividing the power transferred across the air gap, that is power corresponding to the speed voltages. That means this term, this is the second term is the power, then if we want to make it torque, so it will be Te is equal to 3 by 2 psi d Iq minus psi q Id into omega r upon your omega mechanical, because this is your power, and power generally we know torque into speed. So, T into omega mechanical is equal to 3 by 2 psi d Iq minus psi q Id omega r. That means this second term, right, this second term. So, that means this is my torque equation. So, or you can simplify omega r upon omega mechanical. Earlier we have seen this is nothing but the number of field poles by 2. So, it will be 3 by 2 psi d Iq minus psi q Id into Pf by 2, right. This is equation 75. Now, the flux linkage equation, that is 64 to 69, associate with the stator and rotor circuit together with the voltage equation, that is 70 to 72 for the stator, and the voltage equation 50 to 52 for the rotor, and the torque, that is equation 75, actually describes the electrical dynamic performance of the machine in terms of dq0 component. So, all this equation basically 64 to your 75, all these equations actually represent the dynamics of the equation related to the dynamics of the machine. Much more detail we will see later, right. Now, physical interpretation of dq0 transformation, why we do so, that is the physical interpretation. Now, combined MMF wave due to the currents in the three armature phases travels along the periphery of the stator at a velocity of omega s radian per second, right. This is also the velocity of the rotor, because the rotor is in synchronous speed. Therefore, for balanced synchronous operation, the armature MMF wave appears stationary with respect to the rotor and has a sinusoidal space distribution. This also we have discussed before, right. Since a sine function can be expressed as a sum of two sine functions, right, the MMF, this also we have seen, the MMF wave, MMF d axis, MMF q axis, right. The MMF due to stator windings can be resolved into two sinusoidally distributed MMF waves stationary with respect to the rotor. So, the one has its peak over the d axis and the other has its peak over the q axis. This diagram we have seen earlier also, right. Therefore, it may be interpreted as the instantaneous current in a fictitious armature winding which rotates at the same speed as the rotor and remains in such a position that its axis always coincide with the d axis. The value of the current in this winding is such that it results in the same MMF on the d axis as do actual phase current flowing in the armature windings. A similar interpretation applies also to IQ, except that it acts on the q axis instead of the d axis. This certain thing, this is the physical interpretation. The MMFs due to Id and Iq are stationary with respect to the rotor, right, and act on paths of constant permeance. Therefore, your corresponding your inductances LD and LQ, that is D axis and Q axis, are constant. For balanced steady state conditions, the phase currents may be written as follows, right? We can write IA is equal to Im sin omega st plus phi, IB is equal to Im sin omega st plus phi minus 2 pi by 3, and IC is equal to Im sin omega st plus phi plus 2 pi by 3. This is 76, this is 77, and this is 78, right? Now, we know omega s is equal to 2 pi f, that is that angular frequency of the stator current, right? Using the dq0 transformation, so this one, if you go for a dq0 transformation, then this equation id can be written as Im sin omega st plus phi minus theta, because here also your omega st plus phi, right? Now, when you go for dq transformation, id will be Im sin omega st plus phi minus theta. Similarly, iq will be minus Im cos omega st plus phi minus theta. This is equation 80, and I0 will be 0, that is equation 81. Now, we know that because your what you call machine rotates in synchronous speed, so basically theta is equal to omega rt is equal to omega st. That means for synchronous operation, the rotor speed omega is equal to the angular frequency omega of the stator current, right? Same thing. Therefore, theta is equal to omega rt is equal to omega st. That means here if you put theta is equal to omega st, theta is equal to omega st, then omega st will be cancelled, only sin phi will be there and cos phi will be there. So, id is equal to Im sin phi, so it is a constant, and similarly iq is equal to minus Im cos phi, that is also constant, as if they are DC current, right? For balanced steady operation, id and iq are constant, right? So, in other words, alternating phase current in the ABC reference frame appear as direct currents in the dq0 reference frame, right? This is that physical interpretation of your dq0 transformation, right? Now, the dq0 transformation may be viewed as a means of referring the stator quantities to the rotor side. This is advantageous to referring secondary side quantities in a transformer to the primary side by means of the trans ratio. So, the inverse transformation, that is equation 60, can similarly be viewed as a referring to the rotor quantities to the stator side, right? The analysis of synchronous machine equations in terms of dq0 variables is considerably simpler than the terms of phase quantities in the following reasons. Some advantages are there for dq0 transformation. First one is the dynamic performance equation have constant inductances. This is the major advantage, right? Next is for balanced condition, zero sequence quantities disappear, right? For balanced steady state operation, the stator quantities have constant values. For other modes of operation, they may vary with time, and stability studies involve your slow variations having frequencies below your 2 or 3 hertz, right? And fourth one, the parameters associated with D and Q axis may be directly measured from your terminal test, right? So, these are the 4 major advantages for dq0 transformation. Next is the power unit representation. In power system analysis, you have already studied the power unit representation, right? But here for synchronous machine, although we will follow the same thing, but power unit representation will be slightly different, right? And wholeheartedly we will try to understand this. Certain things I will tell you, certain things small derivation I leave up to you also to save some time, but just see how things are, the power unit representation. Now, your quantity in power unit can be defined as actual quantity by base value of the quantity, this you know. Now, power unit system for the stator quantities, right? Now, let us choose the following quantities for stator denoted by subscript S, right? So, we have to choose some your what you call your base quantities. For example, ES base, this is actually peak value of rated line to neutral voltage in volt, right? Then IS base, it is peak value of rated line current, that is ampere, and F base, that is rated frequency in hertz, right? So, this base value. Now, the base values of the remaining quantities are automatically set and depend on the above as follows. For example, omega base, here also we need some omega base, it will be 2 pi F base, that is electrical radian per second. then omega mechanical base, right, that is omega base into 2 by field poles, right, Pf. So that is your mechanical radian per second. Now if it is so, then Zs base will be now Es base upon Is base. Then basically Z is equal to V by I, you know. So Zs base is equal to Es base upon Is base. This is ohm, right. Now Ls base will be your Zs base upon omega base Henrys, right. So actually when you find out, actually we are going to making the base quantities, when you try to find out say reactance of a line, right, you have to do, we make L omega, right, L omega is the reactance. So here also if you multiply Ls base and omega base, that actually in per unit we want to represent. So we represent Ls base and into omega base is equal to Zs base, right. Instead of your reactance type, this is actually Zs base, right. Dimensionally you have to see the correct thing. So Ls base will be Zs base upon omega base. This is in Henrys. Now psi s base, that is the flux linkages. We know psi is equal to Li, right. That means psi s base will be Ls base into Is base, right. And this is your Ls base, and another thing is that can be written as Es base upon omega s base, right. So this is also your known to you, right, because you know E is equal to your d psi by dt in general dimension wise, right. So this one we make Es base upon omega s base. So Ls base into Is base is equal to Es base upon omega. This is Weber turns, right. Now next is 3-phase volt-ampere base. So 3-phase volt-ampere base means we will take 3 into E RMS base into I RMS base, that is the RMS value of the voltage and RMS value of the current. This is capital E RMS, right. So this can be written as 3 into E RMS base will be Es base upon root 2, because we have chosen this your Es base the peak value of the rated line to neutral voltage. Similarly for the current, peak value of rated line current. So when you take capital E RMS, right, so basically this E RMS base we can write Es base upon root 2, and I RMS we could write Is base upon root 2. So root 2 will be 2. So 2 will be your what you call, it will be then 3 by 2 Es base into Is base volt ampere. This is your 3-phase volt ampere base, right. Now torque base, we know torque base is equal to, in general we know power is equal to speed into torque, right, but we are trying to represent the base quantities. So torque base will be 3-phase volt ampere base divided by omega mechanical base, right. So if you and Es, this your what you call this Es Is base, right, here it is your what you call, here it is given that your, this is your, just hold on, this is your psi s base is equal to given, that is Ls Is base into Is base, and it is equal to Es base upon omega base. So here also when you write torque is equal to your 3-phase Va base by omega mechanical base. So in this case this 3-phase volt ampere base is 3 by 2 Es base Is base. You substitute here 3 by 2 Es base Is base, and this is your omega mechanical base. Just simplify this one, you will get 3 by 2 Pf by 2 psi s base into Is base, that is Newton your meters, right. So here already it is given, something is given that your what you call psi s base is equal to Ls base, Is base, everything is given, right. Just you please just to substitute and just to bring this one, that it will be psi s base into Is base. Just little bit to manipulate, you put this one Es base and Is base, and just to make this one omega base your what you call omega r upon omega s base relationship, you put it here, and then little bit to simplify, you will get 3 by 2 Pf by 2 psi s base Newton per meter. This is your what you call an exercise, small exercise for you, right. So this is your torque base. Next is per unit stator voltage equation. We will come now. After making all this small thing, we will come to this one. So from equation 70, this is the equation, Ed is equal to P psi d minus psi q omega r minus RAID. Now we have to make the per unit stator voltage equation, right. We have to convert it. So what you can do is dividing throughout by Es base and noting that Es base is equal to Is base into Zs base is equal to omega a base into psi s base. So if you divide both sides Ed by Es base, so this side also you can divide both sides, that Es base is equal to know that Is base Zs base. So that is your what you call that this is my p psi d. So, both sides we are dividing by Es base. So, Ed by Es base, then this term when you are taking p psi d, we are making it as Is base your what you call omega base, then psi s base. So, this term divided by omega s base, here I have missed s here, right. So, your this thing is omega s base psi s base, and for the second term psi q omega s, here also we are making psi s base omega s base, and last term it is a voltage drop RAID, right. What we are doing is we are making your ZS base IS base, because ES base is equal to ZS base. So, this term also ES base, this term also ES base, but we have to make it per unit form, and this relationship we are using, right. So, with this if you do so, then what we will see? We will see that this ED upon ES base, now ED upon it is a per unit, so we are making ED bar. So, this is actually ED bar. After making all the per units, again we will remove the bar, and from that onwards we will understandable that everything is in per unit, that I will tell you later, ED bar, and this is your psi d upon psi s base. So, this is psi d bar, p into psi d bar then, right, and into 1 upon omega base, and this one psi q upon psi s base, this is basically psi q bar, and omega r upon omega s base, that is basically omega r bar, and this one minus RA upon ZS base. So, per unit, so RA per unit is RA bar, and ID upon IS base, this is ID bar. So, all these things your what you call ED bar is equal to this equation, your what you call the per unit. Whenever putting bar means these are per unit values, right, because ultimately you will find at the later stage things are very simple, and we will make it all everything in per unit. The unit of time in the above equation is second, right, but most in literature also you will find we generally use time in second, but I will show you if you want per unit also time can be represented by per unit time, right. So, time also can be expressed in per units with the base value equal to the time required for the rotor to move 1 electrical radian at synchronous speed, right. So, what we can do is that T base actually 1 upon omega base, because generally omega is a radian per second, radian is a dimensionless quantity. So, it is radian per second. So, T base you will take omega 1 upon omega base, that is nothing but your second, right, that is 1 upon 2 pi f base, right. This is equation 84. With the time in per unit, equation 83, it may be written as ED bar is equal to P bar psi d bar minus psi q bar omega r minus RA bar ID bar. Even time also P bar P is ddt, that is also you are converting in per unit. How I will show you next lecture I am coming back. Okay, thank you very much. We will be back.